Hi, welcome everyone. So everyone here has used image processing at some point in their life. Maybe you added an awesome Instagram filter on one of your photos, or you modified one of your photos, photoshopped it with one of these expensive apps that you wouldn't buy it, or you just took a digital photo. But the thing about it is, how is it even possible? If you think about it, a digital photo, it's binary numbers on a hard drive, but yet the computer somehow figures out this is an edge. I'm going to blur this edge out, or I'm going to enhance this edge and show you an outline of the object in the photo. How does the computer understand the visual world? Today, I'll try and show that using these slides. We'll learn how to do image processing by hand, so to say, because if you know the concept, you'll be able to code it in a system yourself. So the first question is, what is an image? So remember back in primary school, we used to have these coloring books that had outlines around regions and numbers in the middle. You would color in the numbers, and number 2 is brown, and number 3 is green, and you would fill in everything like that. Now, the thing about images is they're really exactly the same thing, although a lot more boring. Those regions, those special shapes, those outlines, they're really just a grid, an exact square grid. The numbers don't really even show color, they show brightness. They tell you that this pixel is this bright. So to make my life easier, I made this simple monitor on my website. It's really low resolution. It can only show 8 by 8 pixels, a color depth of 0 to 7. So that's 8 shades of gray, whatever that means. And so this will make it much easier to work with since it's smaller numbers. So let's see what we can do first. On the left side here, we have the source image. Source image, that's the image that you want to change. In the middle, you have the algorithm. The algorithm you'll use to change each pixel. That's the kind of thing that we want to apply. And on the right side, we have a blank canvas. This is where we'll be writing out our results. Now, you don't want to dirty up your source image by writing results right next to what you're working on, so write it on a new blank canvas. What we'll be doing is converting that source image into black and white. A refresher, it's going to look something about like this. That's what we're going for. Now, the rules are pretty simple. We're going to look at one specific pixel. We're going to compare it to this threshold value over here. Now, if it's bigger than the threshold value, it becomes a white pixel. Full white, 7, the brightest that my monitor can display. If it's less, it becomes a 0. Black pixel, the darkest that it can display. We literally just do this on each and every pixel. So on the first pixel here, the value 1. Is 1 bigger than 4? Well, of course not. So we write down a 0. For the next one, it's 2. 2 is not bigger than 4, so it's a 0. 3, same thing. 6, here it becomes interesting. 6 is greater than 4, so we write down a 7. And so we continue through all the pixels. That might take a while. And we'll end up with a black and white image on the other side. This is the image that's been thresholded. Any pixel value that's greater than this threshold has been highlighted here, and everything else has been darkened out. Now you can see there's a missing corner on that E there. That's because the threshold value, I really chose it at random, very eeny, meeny, miny, moe. Now we can change that, we can tweak that threshold value. If we make it higher, it seems things are getting worse. There's less pixels that are greater than this bigger threshold now. The threshold's 5. So obviously some pixels won't be bigger than 5. So let's try and tweak it lower. Over here at 3, we seem to be getting a good result. So just the right amount of pixels breach the threshold of 3 to show the image. If we keep tweaking it lower and lower, we'll get something worse. Now, the cool thing about this is you can add any algorithm that you like. You can imagine up anything and get some result out of it. Imagine we want to brighten up the image. Every pixel value plus 1. Do it for all the pixels, now it's brighter. Minus 1 to make it darker. It's kind of boring. You can invert the image. You take the maximum color depth, which is 7, minus the pixel value. So we can look at one of these pixels, 1. So we say 7 minus 1, write down the value over there. We'll get an inverted image. It will be the colors will be the other way around. Now, this is cool, but how can we make it better? What if we want to do something that requires more pixels around it? If we look at blur, we can find here that we're going to be using a pixel and its 8 neighbors around it. So as a refresher, blur looks like this. If there's anyone wearing glasses at the moment, don't freak out. The image is actually blurred. It's normal. Now, we're going to take the source pixel, take its 8 neighbors around it, and then sum all those values and divide them by count. Sounds a lot like high school, find the average, a few data points divided by the amount of data points. So what does this look like? If we look at this one over here, we see the center pixel, 0, and on the other side, the 8 neighbors, a bunch of other zeros. Now, if we look at the sum down there, it's a bunch of zeros plus 1 divided by 9. It's close enough to 1, just round it to 1. But that's again because my display can only show 8 different color depths. So I can't show decimals. Now, you write down that 1 on the other side. You go over to the next pixel. You look at that pixel plus its 8 neighbors. It's 9 pixels in total. Get their sum divided by 9. Write it down. As we move here, stuff starts getting different. We get a value of 3 on the other side. This is because there's much more 7s in the sum. So the sum gets much bigger. As we continue on, the values change. Over here, we get a 5. Now, to make sense of this, we'll need to see the bigger picture. But before that, I want to show you something cool. If you look at the value for this 7 here, it's obvious the average is going to be 7 on the other side. So those are unchanged. So what does blur exactly do? If you look at the zeros here, they're also unchanged. But in between, on this edge, we get a value in between those two values. We get a smoother value. What I mean by the speed of the gradient when going over the picture, imagine there's a little bug running from the left of the picture towards the right. It doesn't have to be a bug, it could be a feature as well. Now, it will be on the value 0. And the next moment, suddenly it's on the value 7. It's a large change in color. If we look on the other side here, we see it's been smoothed out. It goes from 0 to 2, 5, and then 7. So this bug has a less steep incline to climb as it goes over the image. It's smoother. There's no high steps in it. So let's see the result of this. From here, you can see all those sharp edges, all those sudden changes in color have been removed. Well, they have been smeared and smudged out. But that's blurring. Now, if we think about this, we can add our own algorithms to this, make something cooler, figure out other effects. But it's kind of hard working like this, using the 8 neighbor pixels and the center pixel. How do you make something bigger out of this? How do you generalize this? What if we multiply each of those neighbors by 1? Sounds silly, it sounds ridiculous, but hear me out. We call this the kernel. We'll be multiplying each of those by 1. Now the idea here is you'll take a pixel on the left image, you will take one of its neighbors, multiply it by the corresponding kernel, and then use the sum of that divided by the count, and then you get an output. So something like this. For this pixel, we're going to multiply it by 1 on the other side, plus the other pixel multiplied by 1, plus the other pixel multiplied by 1. Just follow all the factors through here. You're going to end up with 27 divided by 9. That's really stupid. It's kind of the same thing that we had. But now we can make it better. Now we can add stuff to it. So what if we increase the weight in the middle here? That means the middle pixel will have a larger influence on the final result. Everything will be multiplied by 1, except the middle pixel gets multiplied by 8. Okay, so the normal result that we look at is this, very smudged. That's what we used before. Adding the middle pixel higher will give us a result like this. You can actually see the shape inside there, but yet it's more blurred than this one. So we have achieved blur without destroying the image. That's a good step. Now, one thing you need to keep in mind is when adding these together, it divides by 16. That 16 is relative to the amount of total weight inside here. So if you add all these weights together, you'll get the number you need to divide by, the total weight of the kernel. Now, we can use this to do some awesome stuff. A popular blurring filter is called a Gaussian filter. So this is weighted, but it's weighted more smoothly than I did. It follows a nice circular, smooth bump in the middle, basically. Anyway, at the end of the day, we wanted to do something really cool. What if we change this value in the middle to be negative? What kind of effect are we going to get? If it's negative, we're going to be multiplying these by 1, adding together, multiplying by 1, adding, except when we get there. Now we get 3 multiplied by -4. So it starts giving a weird effect in our image. It starts showing the outline of the region that we're looking at. This is called the sharpening filter. So for the sharpening filter, the color on the image here, why I'm not using grayscale, if you take a look at the values inside the result there, it ranges all the way from -19 to +30. I don't have the amount of color depth to show that. That's why I'm using extra color to kind of show that. If you think about the change here between 0 to 7, how steep that gradient was, over there, -19 to 30 is like really, really super steep. The reason behind this is a highlight of the edges in your image. It highlights where the image suddenly changes color. We can use this for sharpening. This is exactly what sharpening is. What we're going to do is add this together. On the left side, we have the source image. In the middle, we have the sharpening guide, the one we just built. It uses the same kernel that we had over there. On the right side, we have the result image. Now, adding it together is really simple. We look at 1 pixel over here, we add it with the pixel on the other side, and we write down the result. So the source image is 3 at that pixel, plus the sharpening guide is 4 at that pixel, and the result is 7. 3 plus 4 equals 7. That's easy. The next one, 5 plus 20 equals 7. That's correct, right? I aced maths in high school. No, the image on that side can only display up to 7, from 0 to 7. So the pixel values just cap or clip out at those boundary edges. Now that's also the reason why that image looks so ugly on that side. It's really hard to make out. It's like over sharpened. It's kind of a deep fried meme at this point. But we can tweak that. We can scale down the sharpening guide, give it some lower values. By this, I'm just multiplying each of the values by 0.3 or something around there. The slider controls that scaling. Now, as we move it around, we might get a better image because there's less clipping going on. 5 plus 5, it's only off by 3 at that point. It's closer. And some of the other values are well within bounds. Now, I forgot to show you guys what sharpening looks like, but you get the idea. Now, another cool filter we can do, going off from this, taking the kernel and having your position working out, using the position of a pixel relative to another pixel to find its value. Instead of that, we can use ordered statistics. This is where you take the 9 pixels, you order them by value in a linear list, and then you choose the middle value, the median. So we'll take these 9 pixels, order them by value. It's a bunch of zeros, 6, 7. Don't care about that. We take the middle one out of 9. So we take 1, 2, 3, 4, 5, stop. We take the 5th one. Doesn't matter what else there is. And writing that down gives us the result over there. For the next one, we take the middle of those 9 pixels. Same thing over and over again. Now, the idea behind this is we want to remove noise from the image. On the left side image, you can see there's some noise called salt and pepper noise. It's like really dark and really bright pixels. There's white and black pixels, that's why the salt and pepper. So in the really bad cameras, you have noise like that. If you just apply a blur filter, it will remove that noise, but it will also blur out the edges in the image. This has a way of removing the noise without disturbing the regions that much. You still maintain your regions, your object outlines in the original image. So on the left side, there's lots of noise with speckles down there and up in the upright corner. If we look on the right side, we can still see the circle on the left, and the rectangle on the right has seen better days, but it's mostly still there. But the greatest thing is we have no noise over here. It's completely clear. Now, in real life, well, on a high resolution picture, it will look something like this. It looks like it cartoonifies the image. So it mushes up all the colors because it chooses the median. The median is different from the average in a sense that if you add very high values, to your data set, like we have over there with the 5 and the 7, everything is 0, you'd expect the average is close to 0. If you take a normal average, you would get the sum of these divided by 9, which won't be 0. If you take the median, these outliers, they don't matter. It doesn't change the image. It takes, some people believe median is a better average than the actual average. Just because it's more robust, it doesn't care about outliers. You get a more true value in all circumstances, where average easily gets thrown off by outliers. Now, there's another method I want to show you guys. This is going to be quite hard to believe. It's called Fourier transform. The thing about this is the astronaut picture on the left side can be transformed into the star picture on the right side. It is the same image with the same information. You can reverse transform the star image back into an astronaut image. Anyone not believe it? That's good. Skepticism. Now, the idea behind this, the easiest way to try and explain it is to not explain it. It's really difficult. Everyone has watched season 3 Stranger Things. It's like looking at the image from the upside down. It's like looking at an image from another dimension. You really see it from inside out. Nothing makes sense. But once you understand it, it completely makes sense. The image, the star on the right side, it is a display of the image's properties. How much sharpness and how much blur it has. Where the sharpness is and where the blur is. So, the middle of the star, the core of the star, that represents the blurry details of the image. So blurry details in this sense represents color blobs. Any constant color on the astronaut image, that will be represented in the middle of the star. Around the rim, outer edge of the star, you'll get the high pass information, the sharpness information. So anything describing outlines, sudden changes in colors, you'll see that on the outside. Now, at the end of the day, it looks pretty cool, but what do you do with it except for steganography? You can change properties on the star and then reverse transform it back into the astronaut. Then you get the astronaut image without those properties, without some sharpness properties or blur properties. An example, for sharpen, we remove the blurry parts from the inside. We just blot them out of a black circle, and then we reverse transform into the astronaut. Then we get a bunch of outlines. It's literally just outlines, there's no solid colors. For blur, kind of the same thing happens. We blot out everything except the blurry detail. If we reverse transform that, we get no sharpness in our image, no outlines. That's why it's so blurry out here. And if you do something weird, you're going to get a weird result. Don't do this to your family vacation photos. You never know what you're going to end up with. Now, how do we go about doing this? Here we have a source image, same image thing as before. The thing about this Fourier transform is, Joseph Fourier once said, he can draw any shape with a set of sine waves. Not everyone mentions that it's a set of infinite sine waves, but that's only if you want to be exactly accurate. You can do a really good approximation with just a few sine waves. So we're going to be looking at this image in rows. We're only going to be looking at one row at a time. So over there, we're looking at this row. I've converted this row into a graph, a histogram function on the top, Now, this histogram function shows the first pixel on the left is 3. That's close enough. The second one is a 6. That's close. 2, 2, 3, 6. It seems fine. It seems like the same row of pixels. Now, what we're going to do, imagine drawing a trend graph on the top of those bars, on the top of the histogram, connecting the peaks of every bar to the next one. Draw a smooth line over that, a smooth curve to fit over that graph. Now, what Fourier said is that we can add a bunch of sine waves to approximate that trend line. So how do we add sine waves? Some of you might know this. If you don't, here's a 1 Hertz wave, and we're going to be adding it to a 2 Hertz wave. Just pick a specific point in time, like right over there. You can see the pink wave, 1 Hertz, is at minus something, probably minus 0.3, plus the yellow one is at 0 at that point. So you can see the result at the bottom is also negative. It's also minus 0 point something. If you move it on, you can see here, the pink has a large negative, the yellow has a big positive. Add them together, you get basically 0. Now that we know this,
like modulation in the
yeah. Now over here, we're going to be adding these waves together. These are the waves necessary to approximate that way, that line, that trend line that you imagined. But that's only half the waves. We also need to add these together. So add all 8 of these waves together, and then you're going to get something that follows that line up there. Now, it does jump up a bit at certain points, but if you sample that wave at the center of these bars, because remember, a pixel doesn't really have a width. We give it a width. We say the image is this many, it's as big as the screen is wide, so it's got physical proportions to it that the data pixel doesn't have. The data pixel only has a position next to its neighbor. That's all it cares about. Now, we can look at some other examples. It follows those, and those are the different waves you need for each of these. So, what we did in the Fourier thingy previously, removing some of the sharpness or removing some of the blur, the left side is the blurry waves, the blur detail, low pass information. On the right side, it's the high pass information, or the sharpness. So you can literally remove one of these waves, and you won't have that wave's information up there. So if you remove, let's think this correctly, if you remove a very high frequency wave, you will remove very high frequency or very sharp noise. So any sudden change over here, any sudden change like that, a sudden change of color, it will remove that. If we rip out that wave and add them all together again. So what we did in a previous example. One problem with this is one-dimensional. Waves are one-dimensional. The image is two-dimensional. That's why I've only been looking at one row at a time. If we look at all rows at once to convert this to a Fourier star, you end up with two-dimensional waves. It looks like a bed sheet with waves in it. And every pixel here in the image will represent, well, the star image of the source image. Every pixel there will represent one of these bed sheet waves in a different direction, a different frequency, and a different phase angle. But imagine like ripples in the ocean. If there's thousands of these ripples right next to each other and they're correctly placed, you will get peaks and troughs at the correct place so that you can make an image on water. It's really impossible with the technology we have. Physics really needs to go a long way. But in images, it works. When those waves start adding together at a certain pixel, you get a bright pixel, and right next to it, a dark pixel. Like the stuff you see right over here, those changes between those pixels. Now, there's some more cool stuff we can do with image processing. The easiest is, I found this program to be really awesome, but there's lots of other stuff as well. Some of the awesome use cases I've found of image processing. Self-driving cars is becoming a really good thing. Elon hates LiDAR. He thinks image processing is the way to go. I'm with him for that. That sounds cool, image processing. But there's lots of other use cases as well. Most new smartphones, they open up using face detection. You get object recognition using Google Lens. If you don't know that's a chair, it can really tell you that. It's important stuff to know. There's more useful stuff in life though. I found a project that some guys are working on where they want to make an indoor GPS system. Now, GPS works indoor. What's the problem? The problem is when you're 5 stories in the basement underground and you're new at your new job there and you need to find a meeting room on the other side of the building. It's really cool if your GPS could show you the hallways. So this will be able to use your camera, figure out where you are based on the hallways in the camera, the stuff that it can see around you. Matches that to a real map that's been taken off the building, and it can tell you you're in this hallway, this 3-meter radius, you must be around there. And then you can just follow the path, the same as I think half of us did using Google Maps on the way here. Some other cool things is in astronomy. So I have to break it to you guys, but most of the stuff we see in astronomy is fake. No, the Earth is round, none of that. But the thing that we see is these pictures are false color. That's because if you've seen some astronomy videos, documentaries, they talk about telescopes, getting these images through massive telescopes. And they show pictures of these telescopes, and it's a radar dish. How's that a telescope? Because it's looking at radio waves. It's picking up radio waves, stuff that we can't see. It's still photons, it's electromagnetic spectrum. Now, if you color in those radio waves, you'll get a picture just like the pictures I've shown you. They have a different intensity. We just need to give the correct color to the different energies that we actually pick up with those telescopes. Then we can make images. The idea of image processing is if you do that correctly, you mess up your data, you mess up your image. You're going to make wrong assumptions about what you actually see out there. Using image processing correctly, you can color in those stuff correctly so that it actually makes sense and you get the truth out there. So a lot of you might remember the black hole image. The reason it's that blurry is because there's no more information to it. Trying to make it sharper at this point is adding information to it. You're going to get a false truth. You won't get the real truth that it's supposed to be. And lots of the other examples, you can see the colors are quite bright, and that's to make stuff obvious. Now, the last cool thing I found was some guys in university had basically tried to see Wi-Fi. They wanted to make Wi-Fi vision. So I had this little robot running on an Arduino with some stepper motors, and it picked up Wi-Fi more or less in a specific location, a specific direction. So it would point 360 degrees around it, and also it's at 90 degrees up and down, and map an entire hemisphere around it. They basically made an image that looks like this. At the bottom here is the Wi-Fi image. At the top is a panorama photo of the same field of view that this recorder telescope thingy had. So they predicted to see Wi-Fi waves around there because their router is on the other side of that wall. They know this. Now, using image processing, you can overlay this and get something about like this. It shows you the strength of Wi-Fi around you with a hotspot right there. Not a Wi-Fi hotspot, a real hotspot. It's a heat map of stuff around you. So just imagine, when's the next Terminator movie coming out? So I just imagine Arnold Schwarzenegger walking around, not asking for a jacket or a bike, but what is the Wi-Fi password? Thank you guys for listening. So the JavaScript part of this was, this website is all in JavaScript. You guys can visit it and play around with it. Any questions?